In this video, we're going to discuss fluids. So to begin with, let's just talk about what a fluid is in the physics definition. So fluids can include both liquids and gases, and we define it in physics as just a substance that will deform to fit the shape of its container. So if I have some water in a glass and I pour that water into a different glass, the water will take on the shape of the new glass. Both liquids and gases have this property. There are, of course, differences between liquids and gases, but from our standpoint here, we are going to assume that they are both fluids that will shape to fill their containers. One of the key concepts that we need to talk about fluids is pressure. So pressure is defined as the force per unit area applied to some object. So let's think about the importance of pressure by thinking about a needle versus a hand. So imagine that you are standing here and I apply 1 Newton of force to you, but I apply it with a needle. So I kind of, I'm giving you a shot. I push on your arm with a needle. The needle has an area at the end of about 2 × 10⁻⁷ meters squared. This varies a lot depending on what kind of needle you have, but a needle could have this surface area. So that is the area of the very, very tip of the needle, right? So the needle you can think of, and this is not a great picture of a needle, but it comes to a point at the end and there is some area, surface area of this needle. And this is about what it is, right? With this surface area, a 1 Newton force applies a pressure of 50 million newtons per square meter. That's just 1 Newton divided by 2 × 10⁻⁷ meters squared. Okay, that is an enormous amount of pressure. Whereas if I take my hand and apply the same 1 Newton, I get 50 newtons per square meter of pressure, right? So applying exactly the same force over a very small area, like a needle, gives you an enormous amount of pressure. This is why if you are stuck with the needle, the nurse doesn't have to push very hard to puncture your skin, right? Because you have this very, very small area leading to a very high pressure on a very small segment of your skin, and it's easy to puncture your skin with that high pressure. Whereas with a hand, you're getting a very low pressure or comparatively low pressure, right, due to your hand, and that's never going to puncture your skin. This is the same concept as why knives work, right? So if you have a knife, so here's my knife, the sharp edge of the knife has a very small surface area, right? You sharpen it down to a very fine point. Why? Because you can apply a large amount of pressure to your food, right? If you want to cut up a carrot, for example, you can apply a large amount of pressure with a small amount of force, right? So if you want to cut something, pressure is what you care about. Not only can objects apply pressure to other objects, but in fact, the atmosphere is applying pressure to you right now. So there is something called atmospheric pressure, and this is the pressure, the force per unit area of the atoms that make up the gas in your room right now, in the atmosphere in general, pushing in on you, right? So here's you, and everywhere on you, there is a force pushing in on you, and on average, the force per unit area on you is 101,000 pascals, where a pascal is just a Newton per square meter, right? So on every square meter of you, there are 100,000 newtons of force acting on you. And we don't notice this because we have grown up with it and lived with it all of our lives, and we are just accustomed to having this pressure on us. And in fact, our bodies are designed to have this pressure constantly pushing in, right? So if we were suddenly to go to a place where there was no pressure, that wouldn't be fantastic for our health. So this pressure is constantly pushing in on you. And just to give you a sense of where this pressure comes from, why there is atmospheric pressure, well, if you imagine just a little bit of your skin, right? So I'm just going to draw a wall. So imagine it's the skin on your arm, right? We're getting a very close-up view of the skin on your arm. The air molecules are constantly moving around. The hotter it is, the faster the air molecules are moving on average. So these air molecules are moving around, and they are often bumping into your skin. So for example, this air molecule comes, hits your skin. We will assume that it just bounces off perfectly. So the amount of force that it went in with is the same as the amount of force that it went out with. Well, you applied an acceleration to this air molecule. How do I know? Because its velocity was pointing this way, and now its velocity is pointing that way, right? So the acceleration if I just look at this air molecule, and acceleration was applied on it to the left. Because its velocity was going this way, you applied an acceleration to the left, and it ended up moving backwards. Which means that you must have applied a force on this air molecule to the left. But we know from Newton's third law that if you apply a force to the left on an object, then it applies a force to the right on you. So each time an air molecule bounces off of you, you apply a force on it outward to send it back, and it applies a force on you inward. And because this happens billions to trillions of times a second, I do not know exactly how many air molecules bounce off of you every second, but it's a lot. And because there are so many air molecules, this force ends up being distributed uniformly along your skin. And so this is where the pressure comes from. Now, how do we increase the pressure? Well, we could pack more air molecules into the room, right? Then more molecules are going to hit your skin every second. Those molecules are then going to exert a larger force on you, right? We could increase how fast the air molecules are moving. So we could keep the same number of air molecules in the room. We could make them move faster. And then when they bounce off of you, you would apply a larger force to them. They would apply a larger force to you. You would have more force inward, more force per unit area on you, right? So also, this happens, you do not have this pressure. This pressure here, this atmospheric pressure, is just the standard here at sea level on Earth, right? This would change if you're in an airplane, right? Certainly where international flights fly at about 35,000 feet, this is not the pressure in the atmosphere when you're that high up. This is only a value when you are here at sea level. And you can also change the amount of pressure that you feel if you, for example, jump into a swimming pool or jump into a lake. You'll notice if you dive down into a lake that you feel more pressure. You feel more force pushing in on you. That's because the pressure is increasing, and we'll see why as you move down in a lake, right? So you can change the pressure on you in various ways, by going high in the atmosphere, by going down into a lake. But this is the basic mechanism that causes that pressure, and we'll see how we can change it and what the physics behind changing that pressure are, specifically when we look at liquids and going down into, say, a lake, something like that. Another concept that is crucial to our understanding of fluids is the idea of density. Density is defined as the mass per unit volume, so kilograms per cubic meter, of any given object. So water has a density of 995 kilograms per cubic meter. So if I had, a box that was 1 meter on each side, right? So each side of my box is 1 meter. This box, if I fill it with water, has a mass inside of 995 kilograms for that 1 meter of water. If I filled it with air instead, it would only have 1.2 kilograms in it, right? So you could pick up a box of air, because that would only weigh about 1.2 kilograms. But if you tried to pick up a 1 meter by 1 meter box of water, that would be an enormous amount of mass, right? I've also listed the densities of a few other things. So iron has a density of 7,870 kilograms per cubic meter, significantly more than water. You would really not be able to pick up a kilogram or a box 1 meter by 1 meter of iron. That is very, very heavy. One of the things that density can tell us is whether an object floats. So any object that has a density lower than water will be able to float. So for example, vegetable oil has a density just below that of water. So if you've ever poured oil into water, you'll notice that the oil sits on top of the water, and that's because it has a lower density than the water does. We can trade back and forth between density and mass. So if we rearrange our equation, we can find that the mass of an object is equal to its density multiplied by its volume. So let's try to do this as an experiment and try to figure out the mass of the water in my cup. So here I have a cup filled with water, and we are going to attempt to estimate the mass of the water in this cup. So take a minute, pause the video, and see if you can give me an estimate of what the mass of the water in this cup is. So hopefully you have taken a moment and actually done out this calculation. The basic idea of what we're going to do is, we know the density, so all we need to do is find the volume of the water in the cup. So to do that, I'm going to make a few simplifying assumptions. One, I am going to not look at the actual shape of the cup, which made a bit of a V. I'm going to turn my cup into just a cylinder. Right. So here's my cup, it's a cylinder. All right. The water went up about this high, right? 2/3 of the way up the cup. If I just look at the cup, eyeballing it, I am going to say that that is about 15 centimeters between the bottom of the cup and the water level. So we're going to call this distance 15 centimeters. And if I look at the top of the cup here, well, I am going to estimate that the diameter of this cup is about 10 centimeters. Now, my numbers might be off by a bit. The diameter of the cup might be 15 centimeters and this height might be 20 centimeters. But I'm looking for a rough estimate, so I'm not terribly worried about that. So if I'm looking down at the cup from the top, it looks like a circle. And I estimated that the diameter was 10 centimeters, so I'm estimating that this is 5 centimeters. So now, if I want to find the volume, it's going to be the area here of the top of the cup multiplied by the depth. So my volume is going to look like area times height or depth, which is going to be pi times 5 centimeters squared multiplied by my depth of 15 centimeters. Now, I want to be careful because these units are centimeters, but my density measurement is in meters cubed. So I need to change all of my centimeters to meters. So this is going to be pi times 0.05 meters squared times 0.15 meters. Plugging my values into the calculator, I get 0.0012 cubic meters as the volume of my water. And multiplying that by the density of water, I get a mass for my cup of 1.17 kilograms, which is just over 2 pounds. And again, this is a very rough estimate, but 2 pounds isn't that far off from what the mass, or sorry, from the weight, right? If that's kind of the units that I normally think about as 2 pounds, that's not that far off from the weight of that water, which is 1.17 kilograms here. Okay, so we should be able to transition back and forth between density, the mass per unit volume of an object, and the actual mass of that object. Of course, if I give you a mass and a volume for that object, you can calculate that object's density as well.